D and F block elements. Okay. So let us first start with the D block element. Okay. The elements in which the last electron goes to the penultimate. Penultimate means 1 but 1. Means what? Or n minus 1 d orbital. Are called the block elements. Okay. This is definition. It spreads from group 3 to group 12. These are
Sir, ওটা কি লিখেছো স্যার? Electron goes to the
penultimate. Penultimate. Penultimate means last but 1. Penultimate or n minus 1 d orbitals are called d block elements. It spreads from group 3 to group 12. These are also known as transition elements. Okay. Now, definition of transition elements. The elements which have one or more unpaired electrons either in their elemental state or any of its any of their ions are called condition let me write. There are 4 series of D block elements. Okay. First series or 3D series. It starts from scandium, okay, atomic number 21, to zinc, number 30. Then second series or 4D series. It starts from yttrium, yttrium, yttrium. 39 to cadmium, 48. Then third series or 5D series. See, if you there are 10 groups are there. The group 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So you will find difference is 10. Now when you go to third series, it starts with lanthanum. Atomic number 57. To mercury 80. See here, the difference is not 10. Why? After lanthanum, you get a series of 14 elements, which falls in F block. Okay. Because of that, we call them as inner transitions because it occurs within the transition elements. Then fourth series or 60 series. So here also, see, it starts with actinium. And it finishes at CN. It is 112. না না ময়লা বাইরে রাখছি ওইটা অল্প আছে তো ওটা মাছের প্লাস্টিক আছে না এরকম ঢুকে দিবে এইরকম ঢুকে দিচ্ছে CN. This element I do not know whether you have come across. So it is called copernicium. Okay. Copernicium is being named after the astronomer Copernicus. Only one piece there. Copernicus. Named after Copernicus.
Yes, sir.
Now, see, some questions may come from here itself. See here. Though zinc, cadmium, and mercury belong to D block elements, yet these are not considered as transition. Okay. Explain. So what should we write now? What is the definition of transition element? They must have unpaired electrons. So what is the answer? Answer is zinc, cadmium, and mercury do not have any unpaired electron or electrons. In their d orbitals, either in atomic state or in their atoms. So they are not considered as transition elements. So these are not considered as transition elements. See, next. Copper, silver, and gold have n minus 1 D10 configuration. See, n minus 1 D10 configuration. That is, they don't have any unpaired electrons. But yet, these are considered as transition elements. Why? So answer is these elements in any of their oxidation state have unpaired electrons in their d orbitals. So these are considered as transition elements.
Yes, sir.
general properties of tensions. 1. Atomic and ionic radii. See, very interesting. We know, we have seen in p block elements that when you move from left to right, atomic radii decreases. Because we know as you move from left to right, you go on putting one proton inside the nucleus. And along with addition of electrons in their valence shell. So when you put proton, the attraction of the nucleus for the outermost shell electron increases, and by which the atomic radii decreases. Why? Because with the addition of electron in the nucleus or nuclei, effective nuclear charge increases. P block element starts from group 13, ends with group 18. So we have found this property from group 13 to group 17, because in case of group 18, we do not have covalent radius. We go for the van der Waals radius. So that is a separate factor. So similarly, same thing should happen here. In case of transition elements who starts from group 3 to group 12, it has consists of 10 groups. So successively you are putting 10 protons one after another. So in that case, the atomic radii should decrease slowly. But it is very strange, you will find. In case of the transition elements, the decrease in the atomic radius is very, very less. And after some time, it is almost become same. And at the end, atomic radii increases. So this is a very interesting thing which is happening in the transition element. Let us try to understand. So right now, yeah. Right. The atomic and ionic radii. What ion we have generally take? We find that the stable state is +2 of transition elements. Decreases slowly and almost become similar at the middle and and at the end increases slight. That is, we can say it is like this. All right. So we can write here now For example, say it is scandium, okay? It is 144 picometer. Titanium, 132. Then vanadium, 120. Then chromium, 117. Then manganese, 117. Then iron, 117. Then cobalt, 116. Then nickel, 115. Then copper, 117. And then zinc, 125 picometer. Okay? Oh, forget about picometer, you know it. No space to write. See. Question why it is like this. See. So let us try to understand. Don't write. See, in transition metals, by definition, what we say? Here the electron starts moving, going to D block. Okay. So it is n minus 1D. Okay, now see. So scandium, 1 electron will come. Moment you have put 1 electron, that is 1 proton has gone inside. No. So then when you come to titanium, 1 electron also come. Effective nuclear charge is increasing because of the proton. Then vanadium, again it goes. So again that contraction has taken place. Then comes chromium. See. So it will go. Moment you go to this, look. In this case, what is happening? Try to understand. This is s orbital. This is p orbital. This is d orbital. You know, please remember, the size of the d orbital is bigger than p orbital. Size of the p orbital is bigger than s orbital. So this is the nucleus. This is the nucleus. When you put the electron here, along with that you put a proton. So this positive charge of the proton is immediately being neutralized by the negative charge of the electron. In this case, electron is little far. So in that case also, the positive charge of the nucleus, because of the addition of the proton, it is also being neutralized by the electron here, but it is little far. But in case of d orbital, electron is very far. Theoretically, +1 and -1 is equal to 0. But practically it is not happening. Why? Electron is so far, so in that case, that electron cannot immediately neutralize the entire positive charge in the nucleus. So gradually what happens? When you move from this, and this, build-up of the positive charge is taking place in the nucleus. So it cannot happen because atoms are always electrically neutral. So how to neutralize it? So immediately nucleus starts pulling all the orbit nearby. Okay? Moment it pulls all the orbit nearby, then the size of the atom starts decreasing. Okay? So that one you call it improper screening or shielding. See, when you put one electron in this d orbital, theoretically this electron should immediately neutralize the positive charge, but it is not doing its duty. By this time, the second electron goes inside. So what should have been the duty of the first electron? Duty of the first electron is supposed to neutralize the charges of the nucleus before the second comes. But first one did not do its duty properly. Second electron already enters. So what happens now? The second electron has to face the consequences of the incomplete task done by the first electron. Okay? So what do you call it? The reduction of the atomic radii occurs because of improper screening of one d electrons by the other, and hence the reduction takes place. Now the question is, why it becomes almost 7 equal? Look, when you go, then these electrons are getting paired up. So moment you put 2 electrons, repulsion starts. Then you put another one, further repulsion takes place. When the repulsion takes place, then to avoid repulsion, the orbital starts moving away from each other. So it was initially like this. When the pairing up takes place, to avoid repulsion, again they move away from each other. So in this case, two types of forces are operating. One, because of higher effective nuclear charge or improper screening of the improper screening by the d electrons, atomic radius decreases. And what is the second factor? Second factor is nothing but the inter-electronic repulsion between the d orbitals. So the two forces are operating, but they are opposite to each other. So that leads to a stability in the atomic radii. And ultimately, in case of zinc, what is going to happen to zinc? See, all the orbitals are filled up. They have maximum repulsion. So it increases. Okay? I feel I could make you understand. So let me write. So right now, d orbitals are larger than s and p orbitals. The electrons of the d orbitals remain at the periphery. Is it the spelling correct? Periphery?
Periphery, sir.
Oh, yes, correct. I was also thinking. Um, See, what is the meaning of this one? See here. Electronic configuration is ns2 n minus 1 d. Okay? I'm not writing anything. It is 1 to 10. See, practically n minus 1 d orbital is within the s orbital. S orbital is the last, and d orbital is here. But if this is a d orbital, see, it is the orbital is like this. So if nucleus is here, electron could have been here. No, this electron remains here. Just in the classroom, we always like to sit in the last bench to remain away from the teacher. Okay? So remains at the periphery, which leads to improper screening of the nuclear charge. Improper screening of the nuclear charge. So, in order to balance nuclear charge, the orbitals with electrons come closer, leading to contraction of atomic radii.
That part. So in order to balance nuclear charge, the what, sir?
So in order to balance the nuclear charge, the orbitals with electrons,
Oh, okay.
the orbitals with electrons come closer, leading to contraction of atomic radii. Read that now. With gradual pairing of the electrons in d orbitals, inter-electronic repulsion occurs.
Sir, ওটা কি with gradual?
With gradual pairing, of the electrons in d orbitals, inter-electronic repulsion occurs. So there are two forces operating inside. And each opposes, okay, I'll write down here. Two forces operating inside. What are those? Improper screening of nuclear charge and inter-electronic repulsion. NR and opposes each other. This leads to similar atomic this. At the end, inter-electronic repulsion. Let us write here zinc becomes maximum. Leading to expansion of atomic radius. So this portion is little delicate or is little tricky to understand. the ionic radii. In this case, generally we take common, M2 plus. Follow the same trend. As the atomic radii. See, transition in P block we have studied similarity of property along the groups. But very interesting thing is, in case of transition elements, they show similarity of property along the groups. Why? Because they have same electronic configuration. But transition element shows more similarity in along the period or series. Why? Because they have the same atomic radii, almost similar atomic radii. So write a note. Transition elements show similarity in property along the groups due to similar electronic configuration. Second, they show more similarity along the series due to very small difference in their atomic. This is a unique property of transition.
Sir, what's that, sir, in the y-axis, sir?
Melting point.
Oh, thank you, sir.
See here. In this case, what happened? Melting point gradually increases. Suddenly it falls down. Again it increases. Then it decreases steadily. Hmm? The melting point, other series are there, draw from the book. Huh? Melting point of the transition metal increases. Gradually. Then it drops in the middle. Okay, like manganese, technetium. Huh? Oh. Other series will have the same thing. Huh? Drop on the book. And again,
Sir, in the middle এর পরে কি লিখেছো?
the melting point of the transition metals increases gradually. Then it drops in the middle, within bracket manganese and technetium. See manganese. Other series I did not draw, huh?
আচ্ছা, okay, sir.
Middle. And again increases, followed by gradual decrease. Now, why it is like this? So let us discuss point by point. See, in metal, atoms are being held by with each other by metal-metal bonding. And bonding can only occur through unpaired electrons. So in transition metal, what do you find? Okay, I'll draw it. Try to understand. Don't write. Because everything you write now. Scandium 21. It is argon. Before that, noble metal is argon. Okay. This is 4s2 3d1. Then titanium 22. Don't write. Argon 4s2 3d2. See, this is unpaired. This is not, D2 means not paired. It is 1 1 like this. Then comes here scandium, titanium, vanadium 22. It is this. So it is 4s2 3d3. Then chromium 24. Okay. Now we know it very well. 4s1 3d5. Then comes manganese, 25. Don't write. 4s2 3d. See here. When you move from scandium up to chromium, number of unpaired electrons are increasing. So it is like this. Say this is 1, 2, 3, 4. Chromium is 5. So another chromium will come and they will form bond like this. What happens now? When the interatomic bonds are forming more and more, you require more energy to break and separate them, because whenever you melt, substance starts moving away from each other. So until and unless you don't break the bond, they will not move. So what should I say now? The gradual increase in melting point is due to the increase in their metal bonding. Which depends upon the number of unpaired electrons. So up to chromium it goes. Chromium has the maximum bonding. How many unpaired electrons it has? 1 at 4s and 5 in the d. So chromium forms 6 bonds within them. Strongest bond. So it is the highest melting point. Okay. Now please try to understand, then you'll write. Now in manganese, why does it drop? See here. Manganese has very stable electronic configuration. See, it is completely filled and it is half filled. When the electronic configuration itself is so strong, so in that case, they are self-sufficient. They don't have to depend on the neighboring atoms. So in that case, the metal-metal interactions become weaker. See, when we are self-sufficient, we do not take help from our relatives and our neighbors. Okay, we remain in society, but we always maintain our individual identity. All right. Only those who are insecure, they take their help. Insecurity in atom is what? Unpaired electrons. So in that case, what is going to happen? Not only manganese, when you go to the next series, you will find technetium also has stable electronic configuration. So in that case, their intermetallic or interatomic interactions are weaker. So I'm going to write. What will write now here? Sudden drop in melting points of manganese and technetium can be attributed to their stable electronic configuration. So what should I write now here? NS2 N minus D which makes their inter-atomic interactions weaker. Okay. Why the melting point of zinc is so less? Because in zinc you do not have any unpaired electrons. So they have the weakest metal-metal bonding. Okay? Zinc has the least melting point because it does not have any unpaired electron and has weakest metal-metal bond. Take care of this. D block I have to explain maximum. Can I have the upper portion?
Yes, sir.
Achha, खूप भालो.
Yes, sir.
Hey, Vansan, do you have to go to school? Huh?
No, sir.
Enthalpy of atomization. What is the meaning of atomization? See,
স্যার ওটা কি লিখেছো স্যার does not এর পরে zinc has the least melting point because it does not
oh, does not, sorry. Does not have any unpaired electron. Does not have any unpaired electron and has weakest metal-metal bonding. So it will be has, I think. Does not has. Here, Vansan, what will have? Has or have?
have হবে তো
Have.
Have, sir.
I don't know. See here. What is the meaning of atomization? See, When you take a substance, like suppose water is there, or suppose alcohol is there, or benzene is there, when you expose, does it not goes to the vapor state? When they go to the vapor state, they go in the form of molecules. And that process is called evaporation or vaporization. But we know metals made of atoms. So when you heat them and boil them, the vapor of the metal also escapes. But in the vapor of the metals, molecules are not there, atoms are there. So because of that, we call it enthalpy of atomization. That is, here we have discussed the melting point. Here we are going to discuss the boiling point. All right. So same thing, whatever trend that you have seen in case of the melting point, same thing you are going to find in the atomization. So what will happen? In this case also we will find the enthalpy of atomization will gradually increase and up to the middle, then it will drop, again it will increase and then decrease. So it's going to have the same trend. Okay. The transition elements in general exhibit higher enthalpies of atomization. The higher values of enthalpies of atomization may be attributed to the presence of large number of unpaired electrons in their d orbitals. Which leads to stronger metal bonding. Then what should I write now? It gradually decreases at the end due to wearing due to pairing of electrons in d orbitals or weakening of metal bond. Remember, because as the number of unpaired electron decreases, bonds also become lesser and lesser. Okay. Hey, so much I cannot write. Okay then. Bye for today.
Thank you,
Thank you,
sir.
sir.
Thank you, sir.